Hi guys, welcome to the new video energy balances. We are going to leave behind material balances and start energy balances. So yeah, in general there's a equation for energy balance which is sigma delta U plus delta E kinetic plus delta E potential is equal to Q, which is heat, minus work shaft minus workflow. Now there are some conventions which you need to keep in mind. Q is considered positive when heat is flown into the system. Work is considered positive when done by the system. So this is one thing. So let's say that these things are zero, then Q equals to WS, which means water heat is given gets converted into work. So that's how you remember the convention. Okay, now there are few things in this. Let's say that the process is continuous, so something is constantly coming in and constantly going out. So you define something called U hat, which is U by M dot. Whenever you have something dot, which means it is fluid with respect to time. So you define U hat as internal energy per unit mass flow rate. So that's how you define U hat. So you can replace everything over here by hats and q by q dot by m dot, and then you have one more definition that says u plus pv, which is the flow work, is equal to h, which is the enthalpy. So in general, if there are not many kinetic energy differences and potential energy differences, and there is no shaft work is basically rotations and all. So if there's no rotations, there is no kinetic energy, there is no potential energy, then you can say delta U plus work flow is equal to Q, and you can write this as delta H equals to Q, which is the general equation, which will be most. This is actually the most useful equation which you get. Okay, now let's talk about some things that from where, if you are given a question, what are the approaches to solve it. So there are something called steam tables. Steam tables basically are a set of data for a given temperature and pressure. You'll have for given temperature and pressure, you'll have h hat, you'll have u hat values, and then you can take h2 at a state 2 minus h1 at a state 1 and do delta h. So that is called a steam table. Steam table, as the name depicts, is for water vapor. Now there's one important point about steam tables and enthalpy in general, that you cannot define absolute enthalpy or absolute internal energy of something. It is with respect to reference. So let's say I define U at a temperature T is equal to U at a temperature T naught plus delta U from T to T naught. And then I say that I choose temperature T naughts, and at this T naught I say that U of T naught is equal to 0. Then UT will directly impact delta U, and this can be calculated from experiments. That is what is present in the steam tables. So yeah, so this temperature where U is 0 is called reference temperature for internal energy, and wherever you consider H to be 0, that is called reference state for uh, enthalpy. So now one thing you see, that if I say H2 minus H1, so basically this is with respect to a reference. So let's say H naught, which is reference final, plus delta H from not final to 2, okay, minus H naught initial, means from the place where I have picked up H1, there H naught is defined at the temperature H naught initial, plus delta H is not, okay, from not initial to 1. So if this thing and this thing are exactly same, what we are seeing in the tables are just these values, right? We see this value and we see this value, we say that these values are arbitrarily taken to be one. So when will this represent actually represent delta h? This will actually represent delta h when this value and this value are same, so that they cut off and you get the difference between these. So watch the crux out of it. Whenever you are considering delta h or whenever you are considering delta u, make sure that the u final and u initial, or h final and h initial, are taken from the same place, such that they have the same reference. If you have different references, delta h will give you an incorrect answer. That is one thing you need to keep in your mind a lot. Then let's consider liquids. For liquids, we know that the rho or the density is almost fixed, and let's say the liquid is flowing in a pipe, and you say that delta u is equal to q is equal to 0. There are not much temperature changes, there is not much heat going in, there's no rotating parts, ws is also equal to 0. And when you put this into the energy equation, what you're getting is 1 by 2 times u2 square minus u1 square. These are not the internal energies, these are the velocities, so better write this as v2 square minus v1 square plus g times z2 minus z1. This is the potential energy. I'm considering potential energy only due to height. And then there's flow work, which is given by this. This is equal to 0. And this is the general form of Bernoulli equation. Remember, this is applied only for liquid because we are considering density to be a constant and we are doing these things. So density is a constant only for liquids, and this approximation is not applicable for gases. Okay. Now there is a small point which says that if delta P is the if there's a change in pressure, what is the effect on enthalpy? For ideal gases, for ideal gases, enthalpy is a function only of temperature, which means there is no change, no effect of pressure. And for real gases, whenever they behave like ideal gases, then there is no effect of pressure. But otherwise, H is dependent both in pressure and temperature. And for solids and liquids, we say that delta H equals to VdP. Okay, there's another point which says that if you have a closed system with fixed boundary, over there, even though pressure is changing, delta P is not equal to 0. You still say that work flow is equal to 0, because is volume is not changing, there is no flow, and we are just saying that this is a flow work. So since there is no flow, you say that work is equal to 0. Okay, then there's a small point which says Cp equals to Cv plus R. It's obvious, you just need to keep this in mind. And delta H, if a constant pressure temperature is then you do constant pressure process is then you do CpdT, and if a constant volume process is done, you do CvdT. If Cp is given, then you go for Cv plus R and you find Cv and you do CvdT. Okay, so I'll end this video here. In the next video, we'll discuss two things. One is psychometric charts, and a video after that will talk a bit about enthalpy due to mixing and reactions. Thank you.